around Newton's time, he came up with this inverse square law for gravity, and he could explain all the stuff that Kepler had worked out, the ellipses of the planet's orbits. He could note the difference between an object dropped here in acceleration of gravity and the moon's orbit. He could work out, the moon is 60 times as far away as the surface of the Earth is from the core, and this thing accelerates in the correct formula 60 squared times faster than the moon does towards the Earth as it goes in its orbit. And so he managed to bring together the obvious effects of gravity on Earth and in Kepler's laws.
Of planetary motion.
Yeah. So he was clearly onto a good thing. Later it was slightly refined by Einstein, but at the time it was widely accepted as a great accomplishment. But there was a problem. Newton found this problem himself. He didn't like it. He said he couldn't see how it physically worked. It's an attraction. And he really wanted to have a mechanism. He wanted mechanical things to be happening. And they talked about it as they talked about a lot of the other stuff that Newton did as the universe being mechanical, and people were worried that this was going to leave no room for free will or God or other things, Same things that happen every time you have scientific progress. So you're going to go through all that because you now understand this thing is a result of physics laws, not someone pulling some strings on some puppets, So anyway, leave that aside. That's a question for another day. Not long after him, a fellow named LeSage came up with an idea that could potentially explain it by mechanical means. And what he suggested was that there is some flux of stuff in space that we couldn't see, and that this stuff, if we've got two objects in space that are going to attract each other by gravity, this flux is coming from all directions from far away onto these things, but the flux that's coming on this one, it makes a shadow onto the other one. So the flux is coming onto it, and the flux is coming onto this one from every direction except where this one creates a shadow.
Yes.
And that shadow means that this is being pushed towards that, and in fact accelerated. All the formulas come out correct.
A shadow of gravity?
Yes. No, a shadow of this flux force, which looks like gravity. It looks like this thing is attracting it, but it's actually being pushed by all this flux of unseen stuff in the universe.
And so it's like a lower pressure zone?
A lower pressure zone, yes, you're creating that. But that was a good idea, and for a while people thought, yes, that's good. And then when they thought about it more, they found problems with it. It's been fought down by a lot of people. Feynman said, yes, it would work if the flux had this particular relationship to frequency, so the frequency of waves in the universe. And it was generally accepted during these times that there was this thing, background radiation in the universe, which is called the 0-point energy and various other things they talk about in physics. It would work, but the problem was it had to have this relationship that meant that as it went to higher and higher frequency, it went off higher, and you seem to have a problem with infinities again, which keep popping up with these things.
Yeah.
And so he said it doesn't seem to work for this reason. In fact, the frequencies don't have to go to infinity. The frequencies we're dealing with the other alternative was that the energy is actually getting absorbed by the thing. So when if you don't have the energy absorbed, if there's just a flux and it's bouncing off, then it turns out that the shadow that's made from this side, there was an equal amount of stuff bouncing off from this side to replace it. Because if you take that away, this thing here isn't making a shadow in any one direction, it's hitting in flux by all directions, it's bouncing off in all directions. And it turns out that when you do that calculation, nothing happens at all.
You
don't get any gravity.
No.
So, but what I'm proposing is that the absorption of energy by the protons and neutrons, as they make smaller harmonics themselves at a very, very tiny rate, is enough. It is actually sucking, and it is actually causing that attraction process through that, because
Yes,
the
because you
waves
have
getting friction to absorb.
omnidirectional
Yeah. The waves going
force
up.
in the universe,
Yeah.
so you don't have a directional force that would create shadows on
Yeah.
particles, but the particles create smaller and smaller harmonics, and
Yeah.
it's those internal small vibrations
Yeah.
that are creating, let's say, an attraction.
Yeah, well, it's not. It's the wave going out is weaker than the wave going in, by 1 part in 10 to the 40, because it's being absorbed to make these smaller waves, and so it is a kind of a shadow. You can look at it like that, but it's weaker. The wave going out is weaker, so there is than the other wave coming in. So there is an imbalance between the ones coming from each side by this 1 part in 10 to the 40, which will cause the equations of
And
gravity.
each body has an omnidirectional aura that changes the energy force
Yeah.
because of what's happening internally with these bodies. So is it something then an internal reaction that causes them to come closer to each other because
It's,
of
no,
what
it's
it comes out from
it's
it?
the energy that's coming from here
Yeah,
is 10 to the 40th weaker than the ones that's coming from elsewhere.
Yeah.
Because it's just passed through that matter.
okay,
Now, this seems like it solved it all, and it looks very nice.
yeah,
But I have to tell about the problem of this. So we did this LeSage Gravity, and it seems that with the knowledge of wave structure of matter and harmonics theory, we can make this work and fit together with various other things like the large numbers hypothesis and so on.
yes,
But we aren't quite finished. Just when it looks like it's working, there's a problem. The problem is, we said that this wave from this particle is going out
yeah,
and becoming an in wave for other particles in the universe,
Yeah.
and that they are doing the same back the other way.
yeah,
But we said that the frequencies, the masses and the frequencies of particles are going up with time. I just had a realization. The mass could be going up because it contains the other wave, but the frequency doesn't. No, the frequency has to go up. The frequency has to go up because we see the light from distant stars, different galaxies, as having a different frequency to our own. That means their waves that are arriving into our particles don't have the matching frequency, so the inwards wave, we've got a problem with it, right?
right,
I don't know what the solution to that problem is. There are various things that we can look at that partly alleviate this problem, but it doesn't go away. There are things that things aren't sitting still. The planets are going around the sun, the sun's going around the galaxy, and all these motions. As the galaxy rotates, if you're another galaxy and I'm a galaxy and I've got stuff rotating, there's stuff that's coming towards you and stuff that's going away.
yeah,
This stuff will appear blue shifted.
Mhm.
This stuff will appear red shifted.
yeah,
This one, not just because of blue shifted, but partly because of that, and partly because it's concentrating the energy because it's catching up with it. You're getting more energy per unit time from that part than from this part.
Doppler effect.
Yeah, and so you're getting we can't just take the average of all the stuff over the place. We have to allow for these motions, and motion means there's a bias towards stuff that's moving towards you, which would tend to increase the frequency that you're receiving. But even when we say that, that's not the explanation, because when we look at distant galaxies, they quite clearly, even though some parts are moving towards us, the whole thing's highly redshifted. So
Yeah.
some parts one will be a bit less redshifted than another part.
Yeah.
But that's happening. So that's a problem with the explanation I've given. If we don't consider the problems as well, we can't work out the solutions.
Fair enough.
We've got a thing that solved half a dozen problems and created one new one.
Okay.
Which tends to pretty much undermine the whole idea.
It's good objectivity.
Yeah. Those things probably also partly explain light. When we talk about wavelengths of light from different objects and stuff that from different chemical elements, for example, we take sodium, and it's used in lights, and it glows with a nice yellow colour. And if you get the spectrum of it in light, where you spread all the colours out over this much, there's this one sharp line in the yellow that it's doing it all at. Now, if we magnify this spectrum, we spread it out more and more.
Yeah.
It's not one line; it's two lines,
Mm.
quite close together.
Mm.
We magnify some more, we've got these two lines. Oh, each of those is not a line, each of those is a more complicated structure, lots of lines in each one. maybe some stronger than others,
Yeah.
and so on. And this is called the fine structure. And this number 137, or 1 over 137, is called the fine structure constant, and it's about some of the relationship between these things. And in the formula, you quite often get things of the form something alpha. It's called the fine structure constant, alpha squareds, or terms for alpha squareds. And if we take 137 squared, quite often you'll get 1 over 2, alpha squared over 2, or something like that. You'll get, if you take alpha squared over 2, it turns out to be 1 over about 35,000. Quite similar to the ratios of the levels that happen in the harmonic theory, right?
Oh.
And in actual fact, when you expand those lines some more,
Yeah.
you do get some even superfine stuff in there. What's it called? Hyperfine structure, and that happens at the next level of that. Now, in harmonic theory, we might explain this by one is what's happening with the nucleus compared to what's happening with the atomic structure, which is at that sort of ratio. And then what happens with that to the next level up, which we would call cells and things that have cells, but not everything has cells. And then we have all these levels. So these levels of structure can lead to this type of thing going on. And we can see it with a star, for instance. Our sun is putting out light, but it's not staying in one place because of the planetary motions around it. It's wobbling about a little bit by about its own size, so there'll be teensy-weensy effects of the light. If you observe its light over a long period, you would find that you would lose that oscillation, and it would just have this fine structure in it. So the same thing, if an atom, if it's going around so fast, we haven't got time to see that the light is actually wandering about.
No.
We're seeing a structure of the peaks where it's strongest. So we're capturing a period of time rather than a point in time. And if we did the same thing with the sun, we would see this happening because of planetary motions. So what I'm suggesting is that all of these things are doing the same thing at different scales, but because of our human timescale perspectives, we see it differently.
The same formula acted out on different scales of size and time
Yeah.
appears slightly different because of our ability to observe great and small.
Yeah.